Okay, good morning, everyone. Thanks for being here. So my name is Shaohui, and I'm a postdoc at MIT Energy Initiative. So today, the lecture I'm going to give is mostly on how to study the flexibilities from the data centers and where are they from, do they even exist, and how could we harvest them if they are there. So the title I actually changed quite a few times. So eventually, I think the rethinking elasticity in computing is the best one because everything we got in this modern, like the data centers, including all the cloud technologies we have, is all like if we root it back to like the almost 20 years ago, it all comes back to this word elasticity. And I'm gonna give a short introduction first to help everyone understand. So how this new type of like the business coming from. So actually, I went through. No, let me take a step back. So I think in order to like the use something like the because we are talking about like the unlock the flexibility from data centers. So that means the first thing we need to do is trying to understand what type of load it is. So that's why I said maybe it's better to take a step back since most of us are probably more familiar with the energy business, not very familiar with the internet or cloud computing. So that's why I think the first part I'm gonna walk through like these fundamentals of cloud computing. And if you guys found really interested in this topic, here are some like the very nice resources I found, and also as the references I use. So the first would be like the two courses from the UC Berkeley, and the second would be the from Carnegie Mellon. They also have a cloud computing course, and the Stanford course, and also the fourth one would be the kind of like a keynote back in 5 years ago by the Amazon CTO. He did a very nice summary about that. But there's a very interesting trend I found by looking through all those resources. Is like if it was like 5 years ago or 10 years ago, when people are talking about this type of topics, well, mostly talking about like the classical cloud or classical data centers. But in the past 2, 3 years, all those courses I found from CMU and UC Berkeley, we can basically see that the topic changed from the cloud to the AI systems. So everyone is talking about AI these days. And we all are using and adopting more AI these days. But what made this happen, like in the beginning? So if we take a look at the history of the data centers and the cloud computings, we could see that the evolution of this computing is just like how we adopt the technology of electricity and eventually forming the electrical power grids and the interconnections 100 years ago. So I guess this is a brilliant people summarized this process into 3 steps, from innovation to the products and eventually the services. And in electricity, of course, I think most of us are quite familiar. So first we developed this kind of like Maxwell equations and Faraday law, and eventually we have these generators and people develop like the motors and the lights. And then maybe at some point, roughly like more than 100 years ago, those super rich people with mansions, they thought, okay, I'm gonna bring electricity to my mansions, and they build their own generators near their house and build some like the transmission lines to their house and to power like the motors, fridge, and the lights. That's where according from the innovations to the products. But eventually when these products become more mature and the cost went down, and then it's starting to become like a service to everyone. So it becomes affordable, and in order to, you just need to purchase a service instead of like building your own grid. You just need to go to like, for example, these days you just go to like a utility and open an account, and immediately you will have access to the electricity. That's how it works. So you don't need to worry about how the electricity is generated, how it's transmitted from like say probably thousands or hundreds of miles away, and the voltage step up from the generators to transmission grid and step down to the distribution grid and eventually to your house, like say 110 volts we are using. So that's become super convenient. So this service is how it's become accessible to everyone. And I think exactly for this AI is where I also experiencing the same type of process. So first, all the technologies, they are innovated even back in the 1970s when there is no internet to everyone. And but this kind of like a things were finally became like the accessible through the AWS like exactly almost 20 years ago. But there's a kind of like a funny story is that so when this happens, because like 20 years ago, I think there were two senior engineers at Amazon back then. They said, okay, we're gonna move back to their hometown in South Africa. And Amazon said, okay, instead of doing that, we really want you to stay. But if you really want to go home, let's just set an office in South Africa and we continue say like the building this prototype of like the remote computing and the services. But this where this innovation and product coming from. But what really makes this cloud computing that's so attracting to everyone is through the idea of like capacity and elasticity. So if we take a look at this right figure here, so that's how traditionally people manage those IT equipments and infrastructure. So if you own a company, you need to have some like computing resources. You have to estimate what will be the peak demand of your company and or the services you want to host, and then eventually purchase the right amount of like equipment and maintain them so that all the demand will be satisfied over time. But then people realize that there is an issue is because those IT equipments, they are so expensive and also very difficult to maintain when you scale up to like the, for example, like the thousands or even millions of servers. So, but what makes this so attractive for both provider and the customer is that when it becomes a service, meaning that as a customer, what we saw is basically we can request how whatever capacity we want in real time. Like we can always change our capacity because the things we see from the provider is that the system essentially have like almost unlimited capacity in the system. So that is super convenient. But for the providers, let's step back to the story I told why this business become like so successful. Because remember, Amazon used to have this Prime Day, and if you are doing this Prime Day purchase like 15 years ago, what the things you could see is essentially it's gonna be have a lot of latency and essentially some kind of like failures. But what is the nice part of having this AWS elastic computing is, so they essentially purchase a lot of servers, but most of the capacities they only need to use is during the Prime Day, which is essentially 1 or 2 days throughout the year. For the rest of the year, they can just rent the rest parts to the other customers, like in on-demand type. So that everyone is happy. So for the customers, they don't need to hire very specialized talents to maintain and running this super sophisticated IT equipment, and because they often fail a lot of times. But for the cloud providers, they also get a chance to say like, we just need to focus on this very specific area. It's just providing very good services to all the customers. So that's essentially where all this data center coming from, like back in the 20 years ago. So since we already mentioned that it's actually very difficult to maintain the really large system like our grids as well. So grid also fails over time in some random locations. And so it is also true that for the data centers of those large networks. So in cloud computing, cost and reliability, those are really two important topics. And also in terms of cost, um, so I guess these days people are all talking about like we really need the data centers to be flexible, and but the truth is the state of the art systems we are having these days, it is quite difficult because the cost and the reliability requirements, those two factors are essentially making these things quite difficult. Why is that? First, in terms of cost, I think economically, we would always love to see the total cost of ownership when we are trying to build a business or business models. And for the TCOs, and also there are two parts. One is the investments you need to invest ahead. That is on the planning stage. And there's also like the operation stage, which is OpEx. That's gonna cover all the operation costs. So in terms of those, when we're talking about the flexibility in electricity these days, specifically for the data centers, the flexibility often they just only lie in a very small part, which is the OpEx. And there are bunch of like the analysis in the past few years and already studied that, for example, this is the latest one I found from the Synopsys. They have like a consulting branch called ANSYS. They analyzed the TCO of the data centers these days and found that the electricity consumption is only roughly like the 10%. But if we also take a look back like probably a couple of years ago, which are essentially more like the traditional data centers, the energy consumption, including both for computing as well as the cooling and other equipments, they are around like the 15%. So we have this rough idea about it. Okay, electricity consumption is only like 10 to 15% in terms of like the operations. So then the question is, if you, let's say you have like the 10% of the flexibility eventually from the data centers, and you want to provide to the grid, and then what is actually the actual impact on the TCOs of the data centers? 10% by 10% is just 1%, right? That's really like the minor parts. That's why traditionally a lot of like the data centers, they just don't care about the electricity flexibilities because the reliability is actually the key parts. So for reliabilities and when we're measuring like the services, the quality of service is usually the metric we calculate for the services. So in order to make the customers happy, the cloud providers have to provide really, really reliable services to their customers. That's, for example, like there's a very famous like the how many nines you have for your customers for your services. If you're providing 7 nines, I think that would be the minimum requirements for the cloud services. That means translated in terms of time is like throughout the year, the outage, the maximum outage you could have is at most around the 3 seconds, meaning that you have to remain super reliable for the rest entire of the year. So meaning that any changes or any tiny perturbations to the services gonna be like a disaster, which I'm gonna show in the next few slides. So and also in terms of the electricity, that's the same. So probably like the maybe 10, 15, or even 20 years ago, we still could see some kind of like electricity outages, but we rarely see them these days because the grid has to be super reliable. Otherwise, it's going to be very difficult to recover. It might even take like the days or weeks for fully recovery. And that's going to be very dangerous because there are some really critical services has to be maintained. For example, like the hospitals, for example, like the chemical plants or refineries. those loads and electrical loads had to be keep running 24/7 and without any interruptions. Otherwise, there's gonna be a huge loss in either cost and even sometimes in the worst case, some people might lose their lives. So that's why this its reliability is actually quite critical. In terms of like the translating to the data centers and or the data center services, we can see that the complexity here. So basically, here is like a simple example on like how this AI workloads is orchestrated. So at the user level, you only need to type like a few words in your command line. For example, I'm gonna launch a job there, but underlying there will be like the different layers of like the softwares and or like the services. And so for machine learning, it's actually much easier, but for a lot of like the other services like the bank, our online, like the web bank accounts, when we manage them and we manage the investments, they're gonna be like a lot of services all the way from the software level to the hardware level, which also includes like, for example, you need to like incur some like operations on the CPU nodes and sometimes on the storage side and sometimes on the database side and essentially on the network side. So they are too sophisticated, and so by adding all these components up, so there can be like a lot of challenges. So there, which means that although from the customer's perspective, we always see like our demands or the requests being fulfilled, but on the underlying there will always be some like the random failures by any random components in this throughout the chain here. So there will be like the minimum time to failures and the minimum time to recovery and a lot of those things. And those are the things that essentially making this data center operations so fragile. So, and by adding up with the cost I mentioned earlier, making essentially the getting the flexibility in terms of electricity is quite difficult to provide like the flexible loads for the grid services. But the things I'm talking about so far is just if we're taking the perspective from the existing models and the existing type of like the services. But next, in the next coming a few slides, I'm gonna talking about like what changes we need to make in order to like enable that those data centers and why it is actually favorable to use them as a flexible loads to the grid operations. But before that, there's another like the synergy I want to introduce in terms of like the between the data centers and the electrical power grids. So exactly last year, there are actually two events that attracts a lot of attentions. One would be the Spanish blackout in around like the, I think it should be April. Yes, yes. So that blackout was pretty horrible, and it lasts. Thankfully, it lasts only like the less a day because, like I mentioned, most traditional blackouts happen in the history usually gonna take like days, even weeks to get a full recovery. But essentially, even for like only a few hours for the blackout in Spain last year, it cost more than 400 million euros. That's a huge loss. And there was another event in a few months later from AWS, which essentially they have like roughly 1/3 of the global market share. They had an outage also less than a day, but it's the estimated loss was more than 100 billion US dollars, which is quite scary, right? Although we didn't see that, but why this happens? So that's because there are so many critical services are now hosted on those clouds and essentially data centers these days. For example, the aviations. a lot of like the commercial airlines and the cargo airlines are interrupted due to this internet outage. And also in terms of, because we're sitting in the university, so the most relevant part would be like the Canvas or Piazza we are using. They also got interrupted a lot. So back then, a lot of students, they were able to submit their homeworks before the deadline, which is probably the worst thing we could imagine if we were students, right? And for professors, that's another thing. Professors also have their expectations on, you should, like, for example, upgrade the grades by some days before the deadline at the end of the semester, right? So the professors, on the other hand, they were also not able to grade the homeworks or exams and upload there as well. So the education also got interrupted, and the money loss also. Also, when this outage happened, I guess it was the midnight here in the U.S. So the U.S. system mostly fine, but it was already in the morning in Europe. So a lot of like the UK banks, their service got interrupted. And what's worse is this crypto mining, trading, this 24/7 market. So a lot of people, due to this crisis, they weren't able to trade at the right time. So many people got bankruptcy because of that. So that's also pretty bad. And the last example I'm gonna get is happen at our home. So these days, a lot of people are using Alexa and the smart feeders to feed their pets, like the dogs and cats at home. So that's super convenient. So just in case you forgot or you need to travel for maybe 1 or 2 days. But during those days, a lot of pets just got very hungry because of network failure. The smart feeder just failed. So they wouldn't be able to feed their pets at home. So at that time, so that's why I'm always like, this is my cat, by the way. I never use smart feeders, but you could see that they'll be very disappointed when these bowls got empty. So this is basically like the examples I gave, like what will happen when this kind of like continuances we have, and why reliability is so critical for both our electrical power grids as well as the data centers as well. But what we learn essentially from those two events and the synergy between them is that the data center operations, they are so important, and so we have to be super careful about providing the flexibilities, because the additional requirements on the flexibilities essentially may have very large impacts on the reliabilities in terms of those very critical services and other business as well. So yeah. So then let's back to the kind of like the global pictures of the data center here. So since we have like a demand surge with this wave of AI heat, so we also see like the very abnormal terms in terms of making plannings in the systems is like the unbalanced increase. So what we see here is like the estimations just went crazy in the past years. So everybody probably could already seen this figure, or in other forms, in the similar forms by different agencies, by different companies. They make forecasts that the increase of the data center loads is going to be like up to 10% to the entire world. And also that's another fun fact is that due to specifically in the US, in the past 2 decades, because a lot of factories are moving out, and so the entire grid remains stable. So meaning that no increase for almost like 15 years. The annual growth was like only 0.1% to the grid, at the entire grid level. But what we see is that just in the past two years, it's just went up, annual growth increased to like 2 to 3% per year, which means like it's like a lot of increase happen suddenly from nowhere maybe. So that's going to be like a huge challenge because you have to provide this additional capacity in terms of both transmission grid planning and the generation planning, distribution grid upgrade. So that's a lot of issues. And third thing is, so traditionally like the data centers, when people are building new data centers, the main constraints would be like the availability of the network, because networks are really big constraints. But nowadays, the electricity becomes like electricity capacity becomes like a big problem. So the increase is also heavily unbalanced. So that's why we can see that most of the forecasted, like the new data centers, are gonna happen in either Virginia regions, which is traditionally most of the data centers located in a small county in Northern Virginia. And why Texas has become so popular these days is just because ERCOT has these additional capacities, and ERCOT probably is the only major grid within the major region in the US that is still very aggressively expanding their capacity in the grid. So a lot of new data centers are going to be built in Texas. So this kind of a growth is also very unbalanced as well. And in terms of the grid services, so I guess in general we can categorize the related like the grid services in three parts, and also they are in different time granularities. The first, of course, is a planning. That would be like the 5 years or even 10 years ahead. That's like where you are gonna place the new data centers. And second would be like the operation level, which is the fast time scales, which would be the data center protections. Because like I mentioned, those loads are so fragile and very sensitive to the power quality they get from the grid. So what happened essentially last year and maybe 2 years ago already is that there's a lot of quite a few like the big events happen as a grid. For example, here showing an example of 2024 is we can see that although the forecasted orange line, which is essentially the load predictions from I believe it's a Dominion region in PJM. So they forecasted the loads gonna decrease. But what happened is the data center loads, they detected that the power quality was no longer that good at a certain time, like within a second. They just trip off. And they use this their own on-site backup generators to sustain their operations, because essentially if the grid becomes unstable, it might be a disaster for the servers. And but when they trip off, if one data center trip off, that's fine. But if like the dozens of data center trip off, that's gonna be like a big problem for the grid, which essentially translated to the actual load curve, which is a blue curve here. We can see that there's actually a 1.5 gigawatts of load loss just within a few minutes. Thankfully, during that time, it didn't cause much big problems. But let's just imagine when the data center loads, their capacity doubled or even tripled in the next few years, and these things happen again, what's gonna happen? So the protection and the the power quality is another big issue. And thirdly, is something people have been noticed before, but really didn't get really big attention to the general public, is the fast fluctuations. So basically the data center loads, because they are electronics, they are super fast, which means that they can also change very quickly. And I'm gonna show some examples very soon. So for example, like, so there's a report last year by Google, is like for one of their traditional data centers, we can see that within 1 minute, there's like a big drop by 15 megawatts. Probably the roughly estimation, the estimation of this data center site, although they didn't mention, but I would guess it's around 100 megawatts in terms of capacity, meaning that there's like 15% of like the ramps in terms of capacity happening within a minute, which is quite dangerous. If everyone is acting this way, then the grid becomes very unstable, essentially. Although they claim that they have this kind of like heuristic ways to manage or orchestrate their loads, so that at least during a very short period of time, they achieve like 47 less power fluctuations that what they claimed. But we can see that those kind of like fluctuations still quite big, although the peaks has been reduced quite significantly within this short time window. But from the bottom of our hearts, we definitely know that we need something much better than that. So that's why with data center growing and growing in the past few years and in the coming few years, grid services starting to become like a requirements. If you want to build new data centers, you have to make sure that there will be like the adequate resources to power the data centers. So that's why starting last year, there's a lot of like the discussions on bring your own generations by building like the co-located generators on site along with the data centers. And also in terms of like the peak load management, the peak capacity management, and also the ramping rates requirements are also becoming like the new requirements to the grid. I'm gonna show in the next slide. And also essentially like in terms of like electricity market, like Pablo just mentioned in his lecture. So there are energy markets, capacity markets, and ancillary services, which are also becoming more and more important because if with all these new requirements, the TCO of data centers are no longer going to be like 10%. Essentially, it's going to go higher and higher, and going to be like very important factors for data center operations. But in terms of the grid, so people already starting to think seriously like what would be the grid risks related to this new data center loads. So I think like the 2-3 months ago, the NERC, which essentially oversees the grid operations in Northern America, their large load task force published like a first white paper essentially. So like identifies like the high priority risks coming from data center loads, starting from like the long-term planning in terms of resource adequacy. If you could not satisfy the new requirements is that if you could not satisfy all the additional requirements, your internet connection request can be delayed to up to like 5 or 7 years, which is pretty bad because semiconductor change so fast, or the CPU, GPU's network change so fast. 5 to 7 years is too long to make plannings. They need shorter, and the solution would be like the new solution is like if you have like the flexible connections, meaning that saying, for example, like a simple example is like I'm requesting 100 megawatt of capacity, but if I can make guarantees like for 95% of the time it's below 80 megawatts, I probably gonna cut in interconnection queues by 3-4 years. So I only need to wait for like 2 or 3 years, which is a quite kind of like a feasible solution for most of the cases, because essentially you also need like the 2 or 3 years to build the data center warehouse and purchase all the equipment, install them, and make the service online. So that's on the planning side. And on the operation side is like there will be unaware ramps, like I just mentioned. So this will be the part that's very interesting. And on the stability side, it's even faster, like the low voltage right through, and essentially the subsynchronous oscillations can be very harmful to the grid stability. Those will be the two topics I'm gonna talk about throughout my own research very soon. So let's taking now I think we already have like a rough ideas on how challenging the problem is, and getting a hopefully getting a very initial understanding on how the data center load is like. Next, I think next we're ready to talk about the flexibility essentially. So why flexibility is important. I think I already mentioned the first part in the previous slides is that there will be like a huge growth as a grid site. So we need these additional flexibilities if this data center loads are gonna take like the up to 10% in 5 years. And second thing is like why flexible operations from the demand side is so important. It's not just about the energy adequacy, which is a traditional demand response we're talking about. So this flexibility essentially is also quite important in terms of stability as well as the grid reliability essentially, although that's not quite intuitive, but we already see in the past slides like those fast oscillations and also essentially like the grid balances, what's gonna happen if we don't have them or if we have these additional oscillations injected to the grid. So the statement here is demand flexibility is very important. And in terms of all the aspects like the energy adequacy and stability and reliability. Okay, next we're gonna go through like a very specific, like I mentioned earlier, right? Why this AI is so challenging. So here is a very specific example, like a simulation of training GPT-3 by a I think it's by a data center owner. So they published this data set and we analyzed that. So we found that, okay, in terms of like the large language model training, there's a big issue is that there's a synchronized operations among a lot of like the servers because let's say if we're only just making some random requests for everyone in this room, it's going to be just like a white noise injected. So it might not be a big issue. But all of us are suddenly synchronized and putting requests simultaneously. So the operation is going to be overlapped. And we're going to see those synchronized oscillations from either making backups of the training process because it's not that stable, like I mentioned earlier, right? So people always need to make backups during the training process. So we can see those checkpoints ramps every few minutes. And there are also like the faster fluctuations because everyone is synchronized throughout the operations. So we need to make communications and we are doing parallel computing. And so there will be like the communication delays essentially. And when we're making these communications, people have to wait a little bit for a very short period of time. So we'll also see a lot of the fast fluctuations here as well. So essentially when we translate into the frequency domain of this time domain signal, we're gonna see like a very clear, like what would be the dangerous signals from the power fluctuations to the grid in terms of both slow oscillations and faster oscillations. And also essentially we could be able to analyze the delays of different type of signals. That's going to be very critical to study the grid stabilities essentially. And then when we have a very nice model of the data center loads, we'll be able to, or specifically this type of AI loads, we'll be able to propose solutions to that. And in my own research and collaborate with Deep, who is another research scientist at MIT, we are coming up with this coupled elastic scheduling of the data center load scheduling. The high level idea is, which is essentially like in some of the loads in the data centers, they are not flexible. So what we can do the best is we make forecast of those type of loads essentially on the red parts and making the capacities for them, like also very similar to the day-ahead energy market calculations by solving optimizations. So we know what capacities we're gonna schedule in the next 24 hours, for example. And the rest of the parts, because some of the loads are essentially flexible, so we could essentially making the plannings according to the demand there, and so we can smartly use the capacities to analyze which hours is the best or the most economically optimal way to place them and for those flexible loads, essentially. And there are some additional things we can do is because we figure out that those are actually not enough. Probably only provide like the less than 10% of flexibilities. So can we do better? The answer is yes. So because essentially the system itself is also kind of like elastic. So here's actually a very simple example I can show if it's there. Oh, okay, maybe I should. Yeah. So let me see if we can see it from here. Oh, not this one. So our computers are not running in the static mode. So we can see that the frequency of our CPUs is always changing. So the underlying operation is always very flexible in terms of how much power we inject to the chips. But for the data center, it's slightly different because we're making it reliable as much as possible. So it always mostly running at a very specific frequency, drawing the constant power and voltage. But essentially, for a very short time period, we can also adjust them just like what we do as a laptop in order to make it more energy efficient. That is what people call it the dynamic voltage and frequency scaling. I think in the next, I think it will be the last lecture. The Yifu is gonna talking about more details over there. So essentially, in our research, we figure out that not only from the data center load schedulings, but if we have some additional fast resources like the energy storage, it's gonna make the flexible operations in the data centers really powerful in order to satisfy all the additional grid requirements while providing some additional revenues by participating in the energy markets. And yeah, so that's the rough idea. Specifically for the computing load side is, let's say, okay, since we already discussed quite a lot about it, so we have this very good understanding of data center loads, so we can essentially safely formulate like a model to optimize the operations. And the general idea is just penalize delays on the flexible jobs because we always have like a deadline for each type of jobs. And if we pass the deadlines, we're gonna penalize on that. And if the planning cycle ended, it's still not finished, we're gonna impose like the even higher penalty on that. So why is that possible? Because like I mentioned earlier, but here's a more specific example, like what type of like the jobs they are more flexible and some of them they are not flexible is, for example, like the web search, it's like a real time, so it's never flexible. And for some like the video streamings or large file transfer, those are slightly flexible, but people are usually not very tolerant about the delays. So we cannot delay them too much. And for something like the AI model training and or like the video processing, we can essentially wait a little bit because for like the training, for example, because it's not like a real-time service, so there are some kind of like a flexibilities there. And for other like the big data analytics and or batch processing jobs, those are super flexible. So some jobs can wait even a couple of days. So those are the flexibilities we could get from the load modeling side. And since we talk about the battery, so we also need a very good battery model here. So battery model is more intuitive and most people already understand in many cases. But what's the nice thing here is we advocate that apart from the traditional energy arbitrage, which is essentially just trading the energy market, The batteries, those are very powerful and the fast resources. They can essentially also participate in the ancillary services, which are also very profitable. And in many times, you only need to provide the capacity to the market, not just in a standby mode. So those are the most suitable ways we find those additional benefits for batteries. And but battery is also not a free resource we can use. Batteries are just like the servers, are also expensive equipments. They have their own, like the degradation risks as well. So for example, like the Teslas these days, they say there's a maximum operations you can have is like 150 cycles per year, which is essentially roughly like a 0.5 cycles per day. And those could essentially put some additional constraints on the battery operations as well. And translating into mathematics, I'm not gonna talk about the too many details on here, but it's basically how we model in the mathematical way about the ideas I just mentioned. And so those will be like the penalty terms in the objective in terms of like a computing load delays and also the battery degradations as well. And the first three terms are with respect to the energy markets I mentioned, the energy market and the ancillary service market in terms of like the reserve and the flexible rampings. And this is how the energy markets are evaluated and the uncertain realizations, because essentially we are making plannings and there will be uncertainties happen over there. And then there will be additional requirements on the grid interconnections in terms of the peak demand as well as the peak ramping rates. And lastly would be like the different categories in terms of like computing load operations, battery operations, and the grid services. So this is like a very interesting formulations, but it's quite difficult to solve. It is a robust optimization. It's a mixed integer nonlinear programming. So I think due to the limit of time, I don't have enough time to explain all the details, but anyway, you are interested, I'm happy to answer any questions in details after this talk. So the case study, I think that's the most interesting part. So in one of the early case studies, we already showed that battery is going to be super powerful, but what's going to be the real world performance here? So we actually use some like the real world data we get to run these simulations. So we assume that it's roughly like the 100 megawatts data centers with like a reasonably small size of batteries, so you won't take too much of the space in the data centers. And assume that roughly the base load was around 55 megawatts and the grid limit is 110 megawatts. And those will be the injections, the data sets, scenarios we use. So one is the PDU utilizations from Google that was taken from 2019 from this traditional cloud services. We can see that those are the roughly like the 30, like 1 month. We can say that within a single day, there will be like the at most 20% fluctuations in terms of power. So we need to manage that in order to satisfy the grid requirements. And for the energy market prices, we'll also take the real market prices from both CAISO and PJM for the primary reserve price signals as well as the flexible ramping signals from CAISO in the same month last year. And the results is actually quite interesting. So we set like the roughly 2/3 of the schedulable loads, they are delay insensitive, and some of them are higher priority with less flexibilities. So the results we see here, we can see that actually the net load is quite flat. And it's those like the peak demands are managed by these smart schedulings as well as the additional battery buffers, and those ramps are also controlled. So all the constraints are satisfied. And the battery operations is basically discharge to control the peak ramps and also like the providing this additional capacities as a ancillary services. And the next is even more interesting because there are even more fluctuations here. So those like the, but we can see that the net load after optimization is still quite flat below this grid requirements, and there's no large ramps as well, and those peak ramps are absorbed as well, and the batteries operate in a more aggressive way to incur both charge and discharge operations. And what's interesting is we see all types of grid operations we could see in these models in terms of both reserve markets, flexible ramping up, flexible ramping down, and also charge and discharge operations here. So if any of you are interested, and happy to discuss more details about our model afterwards. So just in order to summarize, I asked Gemini to create this diagram for me. It looks so good. So if I'm gonna do this, probably need like 1 month to learn and maybe a whole day to make this diagram like this. But now just with a few words as a prompt, it will automatically summarize the work I have done and creates this nice figure within minutes. So that's why I think this is a new market. When it becomes like a service, everyone is gonna use that in the next few years, and that's gonna be translated to a lot of like additional services and essentially the loads to the grid. In terms of the fast services, since it's still like a very preliminary research, I'm just show some simple ideas. Like during the trainings, we already show that there will be like the checkpointings and the fast fluctuations on the parallel computing scheduling. And in the inference, we also see this fast rampings and consequences is we need to manage them in the much faster time scale. Because in this scenario, their head planning is not going to be enough because those are all happening in the seconds and even sub-second level. So we need like say faster solutions to that. So that's why we no longer could use this optimization model, but instead we need dynamic models and using the control theory to solve these problems. Still, I think the idea is the same, using the batteries and the UPS, which is essentially already there in the data centers. They will be able to manage these fluctuations, but there will like the additional work to do is right now, people don't understand the load well enough, so we need better load model. And also like this kind of like a new paradigm, we need to co-control in terms of both computing side as well as the electrical side. So we need better power models. And lastly, this new control design is also quite important. So that's rough ideas. And something we've already done is like running real simulations and see what's the, for example, in the inference, what type of oscillations we have here. Those will be like the second level oscillations. Those will be the sub-second level oscillations. So next step is we're gonna try to build like a load model for that. And lastly, this is even in the faster time scale in terms of like sub-millisecond level, there will be more oscillations. There are preliminary study from University of Alberta. So they have this nice EMT power modeling on that. So we are, I did some like the model following their paper and see what's gonna happen if we have this additional supercapacitor, which is essentially already adopted by NVIDIA in their latest NVL72 and 144 system. I think that's another very interesting study we can pursue. Just to summarize what I've been talking so far today, I know it's a lot topics to cover. So the brief takeaway is on the slower time scale. The small battery is going to be very, very useful in managing the peak demand and the ramping rates when making schedules. And the load schedule also is a big plus if we have this additional battery buffer and do the co-optimization on both computing side and the electrical side. And essentially, like for the faster time scale, we need real-time control to do that. There are some like the quite interesting extensions in terms of the applications of this framework. It would be like the physics-guided load predictions and the multi-data center network study by coupling the electrical grid and the data center network as well, because nowadays people are building the gigawatt level data centers, and some of them are centralized in one campus. But most feasible ways, I think what Google and Microsoft is already done is like within a single city, the data centers are located in a very few nearby locations. Each one can be like 300 megawatts each. And essentially the entire system is like the gigawatt level still. And that's gonna bring some additional challenges to this problem as well. But what's essentially gonna happen in the future is just like the water supply network, natural gas network, or the communication networks we already have here today, is in the near future, the data center network is also gonna become a critical infrastructure to our daily life, to all the services we have in our business, industry, and all those networks when are coupled together, we need like a better model and paradigm to make the control, make the planning, make the operations in real time. And lastly, I think there's a very interesting example I got from the talk last year by Tesla people when they're building the XAI hyperscale data centers. They actually tested using the on-site generations because what they requested was like a 500 megawatt capacity, but the utilities only offer like roughly 200 megawatt, if I remember correctly. So those additional generations, they bring their own on-site gas turbines, which is a blue curve here. But we can see those ramps are pretty large. What they do essentially is like for a very short time window, like the 30 seconds, they turn on their batteries, which I think is roughly like a 200 megawatts and a 400 megawatt hour capacity, using that to do fast operations to absorb these additional oscillations here. Those are right now quite dangerous to the batteries because the battery gonna die pretty soon. It won't last like more than a few minutes, then it would be overheating. You have to shut down to make it cool for like a few hours. So, but it did provide us a very promising directions like the running like the co-located resources. There is a way to solve this problem. I guess that's pretty much the things I want to talk about today, but last night I decided to add this additional slide is, let's getting back to the very, very beginning. Is data center a real grid problem? I guess now everyone have a better understanding, so we could have some like the different answers. But for me, myself, the answer to that is yes and no. The yes part is it is a real grid problem. Is right now we don't understand the problem really well. We don't understand our data center loads very well and how to like see synchronously operating different network simultaneously. And also, I guess a very nice thing is a lot of people realize this is a big problem. Like many of you in this classroom, we are working on this problem. So it is a real problem and we can solve it. But it is also, on the other hand, it's not that difficult because we already see we have the solutions already. The theory and the back-end technology and all the requirements are already there. The problem is the changes just happen so fast in the past 2 years. We are just not ready for this sudden change. And what we need to do, I think in my own perspective, is we need to be motivated and make change fast enough because before this kind of a delay in our research and also industry efforts, becomes like a real problems maybe in the next few days, and not next few days, but next few years, right? That's what I'm planning to discuss today, and thank you everyone. I think we could have a few minutes break before the next sessions.
So I don't know if you have any question before we have the break. Yes?
I just want to add a comment. Thank you. I understand data centers are trying to move away from the grid these days because, as you said, because of the reliability and also the cost. So in Virginia, currently the grid takes almost like 5 to 7 years. It's huge, I guess. So maybe one way is to go building what you call the building the meter power plants, I guess, which may take less time, I guess. Just a sharing comment.
Yeah, thank you for the comment. I think that's also people starting to realize these days is in many times right now it's more like a political or regulation problem instead of like a technical problem. So I guess the regulation side need to act faster. And also like in the next sessions, Juan is gonna talking more details on the planning side as well. Yeah, thank you for the comment. Any other questions here?
Question about one of the slides that you showed at the beginning, that you showed there is a 10%, 2% nationwide electricity increase due to data centers. But then there are only 2 states that they're actually getting most of the data centers, Virginia and Texas. So this 2% then national average, it can be totally biased towards those 2 states, right?
Yeah.
So what is the plan exactly for those states, especially regarding what you said that Texas has enough capacity, and apparently it seems it's not a problem there. So how do we manage this, and how are we going forward with that?
Oh, that's a great question. I'm afraid I don't have an exact answer for that because that's also again like it's a very complicated problem. It's in terms of both policy and also the capacity expansion. I think Juan is the expert in that area. So I guess what the point you make is quite important. Is yes, nationwide is 2%, but if everything is focused on a very few spots, that's going to be a much bigger problems to the grid. Not only the grid itself, but also because the network these days is still like a quite big issue. When people are focused too much on the power, a lot of people actually forgot what happened in the last 2 decades is like the network is also a main constraint. And also when you have this additional a few hundred megawatts load at a single site, the cooling is also a big problem. So the water scarcity in many cases is another big constraint. So we really need like a very nice model to tackle all the problems simultaneously. So otherwise there will be big issues very soon. But I guess today, since my background is mostly on the computational side and the electrical grid, so I can only answer the part of in terms of electricity. Yeah.
Apologies if I missed it before, but like I hear sometimes about the different types of profiles for the training workloads and the inference workloads, and inference being more important to be closer for lower latency. Like for the modeling that was done, was that focused on kind of like composite or one type versus the other?
I think right now I am still working on it, but I think for the training it is easier because inference is more like a real time. It has a lot of randomness and it's also a lot faster. But in terms of the training, it's synchronized, so it's more predictable. So I think there are already some like preliminary work on that. Emerald AI and the Boston University, they have some work on that in the slower time scale, but we are curious to learn in the faster time scale in terms of oscillations because oscillation is going to be a big problem for grid stability. So